Hi, welcome back to es301 Engineering Analysis. This is chapter 4, Truncation Errors and the Taylor Series. So here are the learning goals for this video. At the end of this, you'll understand how a Taylor series is used to approximate a function elsewhere. You'll know how to calculate the terms in the Taylor series approximation. You'll be able to determine the uncertainty in a function's prediction due to uncertainty in the input. And you'll understand how truncation and round-off error combine to form total numerical error. All right, so first I want to give some background about why you would ever care about the Taylor series at all. And so effectively, it comes down to sort of the question of predicting the future. So for example, let's look at this baseball player here, and he hits this ball. And the question I have is, you know the ball is right here on his bat. And my question is, some location down, so maybe 100 yards, downfield, I want to know where is that ball going to be. Okay? Well, what you might do, if all you know is that the ball is at that point right there, you might just say, well, I'm just going to assume it's a line drive and the ball is going to be at the exact same height, just 100 yards down. But alternatively, if you see the direction that his bat is going, and you might realize that it's going up slightly upwards, the ball is here, the bat is going upwards, you might say, well, I actually think that the ball 100 yards down is going to be up in this direction because I know the direction that it's going and the current location that it's at. Now, furthermore, you might also know that once it leaves here, it's going to be under the influence of gravity. So there's a little bit of curvature to it, and you might go ahead and approximate it that it's right there. So what you're doing is you're using information at this location, I'll call this at location 0 yards, to try to predict what you are at 100 yards at some other location. And that's the key to the Taylor series. We're going to look at a tool to say, if you want to know it somewhere over here, but all you have is information over here, how well can you do it? And what we're going to realize is we're going to be using this idea of its location and its derivatives in order to predict where it's going to be downfield. Okay, so let's kind of get into a little bit of the math. And so this is a diagram from the textbook. And so what's shown in the black line here is this is the true function. So this is a plot of f on the left hand, on the y-axis, as a function of x. Okay, and this can be any arbitrary function. We'll go ahead and put some concrete functions in here eventually. And so here, this is what we would call the zero-order approximation at the top. This is the line drive, where we're just going to assume, well, if I'm down at some other location further downfield, I'm just going to assume the same location I was upfield. Okay, well, if this is the true function, we realize, well, we've got actually a fairly large amount of error right there in that prediction. Now, I go ahead and use more information at the point that I know. So this over here at x equals 0 is the point that I know. But I also know the first derivative. I would go ahead and approximate it a little further down, closer to it. So what I'd be saying is that f at my new location, that's what the book's saying, f at x at I plus 1, is, well, wherever it is before, I'm going to take the derivative and then multiply it by the step size. And so this value h is effectively downfield over here. So this right over here is the step size h. All right? So that's h right there. And so I'm going to go ahead and take my derivative, multiplying by that direction, rise over run. I'm going to get a better approximation. Now I can keep doing that, and this is what the Taylor series does. I can start using second order or second derivative. So now I have my line drive approximation, my derivative approximation, and then this second term right over here, if you look closely, this is f double prime. That's the second derivative of the function at x. It's over 2 factorial, and then you multiply it by the step size squared. So what you end up getting is a progressively better approximation with each one. So here's the actual equation. Okay, so I want to know it at value of x, and what I'm doing is I'm using values that I know at a. So this is point A. So this is x is equal to a. This is the equation in the book you'll see. So this is my zero-order approximation, f prime at that location times my step size. So that value, that x minus a, is also called the step size h. And then I have my second-order approximation, and then a little bit of notation. My third-order approximation, I'm doing my third derivative. So that's what f to 3 here is. And the reason we do that is if you start putting a whole lot of primes up there, it's kind of hard to see what you have. So a little bit of notation. This is the third derivative of f. as a function of x evaluated at a over 3 factorial my step size cubed, and you can keep going. And this is actually an infinite series, and as I keep adding terms, I'm going to get closer and closer to what my true value is, using only information that I have at that point. A little bit of caveat: if I have a polynomial, you'll realize is there's actually a finite derivative that I can take before I don't actually end up improving that function anymore. So for example, just to mention, let's say that f was equal to 3x squared. Well, you realize after you take the second order derivative, you're going to end up with a bunch of terms that are 0. So all these terms, higher order terms, will be 0. So you can only get so close. So you actually can't get infinitely close, infinitesimally close to the true function with a polynomial function, but you could if you had functions that have an infinite number of derivatives, like things with exponents. Okay, so let's go ahead and do a numeric example here. So what I'm going to do is I want to approximate my function f, and I want to do it at this point at x equal to 2.1. So I'm going to use the values and derivatives at x equals 2. So this is the point that I know, and I want to know what it is at that point there. So here's the function that I'm doing. 3x sine of x over 12 plus x to the 4.5. Right. And so first of all, what I could do is I could just go ahead and approximate, or actually plug in this value at x at 2.1. So let's go ahead and just do that. And if I go ahead and do that, I'm going to have a value of 29.279856. All right, so there's what the actual value is at 2.1. So this is my true value. What I'm going to do is now use my Taylor series approximation. Let's say to reproduce down here. I'm going to keep adding terms and find out how close I get to that point right there. All right, and so let's go ahead and give ourselves a stopping criterion. And so we're going to say when the true error is less than, let's say, 0.01%, we can go ahead and stop doing this. All right. So let's go ahead and we'll go ahead and look at our zero order approximation. We'll make a table. It's first order approximation, second. We'll see how many we have to do here. So first we'll go ahead and I'm going to go ahead and approximate what my value of f of x is. And so first what I'm going to do is just plug in x equals 2 into this equation right there. That's going to give me my zero order approximation, and that number is 23.62279. So 23.6, I want to get to 29.27, clearly not very close. And if I go ahead and calculate what my error is, and I can calculate the true error because you know the actual value right there. So what we're going to be doing is we're going to be doing essentially f at a minus what f at x is all over f at, sorry, we wanted at x, excuse me, at x, to go ahead and find out what my error is. And that number right there, the actual true error, is going to be, I've got that at 19.32%. Alright, so now what we're going to do is we've got to go ahead and add our first order term. So I'm going to take the derivative of this function. So I have to take df dx. So let's go ahead and do that. So what I want to do is I want to do what is df dx. And so if I look at this function up here, I would have the first times the derivative of the second, so 3x times, and the derivative of that is going to be 1 over 12 cosine of x over 12, and then plus 3 times sine of x over 12. So I did first times the derivative of the second, plus the second times the derivative of the first, and then I've got a plus 4.5 x to the 3.5. Right. So there's my, this is df dx, or this is also written as f prime. So I'm going to go ahead and put that in there, okay? And then multiply by my step size. My step size here is 0.1 because I'm evaluating this at 2.1 and evaluating it at 2. And then I'm going to go ahead and add that term. And if I go ahead and do it, my new approximation now is 28.81303, and that's going to give me an error of 1.594%. So I'm getting a little bit closer. 28.8 is a lot closer to 29.7. So we can keep doing that. So first, now I've got to take a second order derivative. So here's my first order derivative. You've got to take a second order derivative of that. So my second order approximation is 29.26094, and that's going to give me an error of 0.0646%. So getting closer, but still not quite 0.01%. So let's do our third order approximation. That's going to give me 29.279506. And that gives me an error of 0.00119%. So now I've got my stopping criterion. I've got a less than that error at including the third order Taylor series approximation, 29.279, 29.279. Pretty darn close. Okay. So that's how I go ahead and do this. Now, first of all, you might wonder if you kind of look back at this and say, why in the world do I go to all this work if I can just plug that value in? Well, this is a little bit of a contrived example because we're trying to just show how you do this. A lot of times you don't know what you are at this other point, and that's what I'm going to go ahead and do and show you where that comes up next. Okay, so this comes up in engineering in the idea of error propagation, right? So anytime you have a sensor that's going to go ahead and measure something, there's going to be some sort of uncertainty in it. So for example, if I have a tape measure, you look at your tape measure pretty close, there's little increments on here, and so there's always a little bit of uncertainty if what you're measuring falls in between this. This is the uncertainty in my measuring device. And all measuring devices have some sort of uncertainty. So now if I wanted to go ahead and measure, so say for example, I wanted to measure the area of something, and I was to put my ruler over here and measure that, I realize I've got a little bit of uncertainty in that location. I put my ruler down here, and I'm going to measure it over here, and again I've got a little bit of uncertainty between those marks, and so I don't know an area that's approximately that right there. There's sort of an uncertainty in the area related to the uncertainty in my measuring device, and that's kind of straightforward and simple to see in terms of something measuring area. But now imagine I wanted to go ahead and measure what the radiative power is from something. Okay, so remember what the equation for radiative power was. If you don't, that's okay. This is the equation here for radiation, where I've got the power, and it's a function of the emissivity, the area. This is Stefan-Boltzmann's constant, and then I've got the temperature of what I'm radiating to the fourth power minus where the ambient location, so whatever it's radiating into the environment. And so if I said, well, what's the uncertainty in the radiative power based on what your uncertainty in your measuring device is? And here it's not quite as obvious because you've got this fourth power in here that I'm trying to go ahead and determine. Okay. Well, you can look at a couple more examples. So if I was to go ahead and hit a steel pipe, for example, with a hammer, I'm going to go ahead and send a sound through here. There's a speed of sound in solids. And so there's an equation for the speed of sound in solids, and it's right here. This is the speed of sound, c, and it's the square root of, and this E is the Young's modulus. That right there is Poisson's ratio, and here's the density. And if I said, well, I can go ahead and measure, for example, the modulus and Poisson's ratio in the lab, and I can go ahead and measure the density. What's my uncertainty in my speed of sound value? Being that there's going to be an uncertainty in all those measurements, again, it's not entirely clear. But what we can do is we can use Taylor series to do it. So remember what we said. Taylor said that F at A is equal to F at X plus dF dx, right, times X minus A. Right? And this was the first order Taylor series. We could go ahead and add some more terms. And so if I go ahead and move that to the side, I have F at A minus F at X. So this is essentially my function. The uncertainty in my function is going to be equal to dF dx times X minus A, which is now the uncertainty in my measuring device. So for example, looking at my equations over here, what I would be doing, let's look at that. At the speed of sound, I would go ahead and want to know the uncertainty in C. Due to my uncertainty in, for example, E, I'm going to take the derivative of C with respect to E, that's this term right over here, times the uncertainty in E, and that's going to give me my uncertainty in the value of C. So let's start with a simple one. Okay, remember, here we had the measuring the area, and so if I want to go ahead and determine what the uncertainty in the area is, so I'll call that delta A. The uncertainty in the area, well, what it's going to end up being is equal to dA dL times the uncertainty in the length plus dA dW times the uncertainty in the width. Right? And so go back, remember my measuring, if this is the length right there and this is the width, and we knew that our uncertainty from our measuring device was more or less that. What we realize is this is my delta W, my uncertainty in the width. This one over here is the uncertainty in the length. And so that's what I'm doing. This dA dL, well, that's simply W, and dA dW, that's simply L. So what we realize is that's exactly what we're calculating there, the uncertainty. It's more or less that. Now, it's not exact because we've double counted this area here, but again, this is only a first order Taylor series. If we take a second order Taylor series, we'd end up starting to eliminate that. But these tend to be pretty small, so we can usually just stop at a first order Taylor series. So let's look at a more complicated example here. So here's the problem that I've got. I want to go ahead and find the uncertainty in the speed of sound, and I've got some material where I know that the Young's modulus, and it's 100 plus or minus 0.1 gigapascals. I've got a Poisson's ratio and a density right there. And so what I'm going to do is we'll assume that the only uncertainty is in E right now. And now what I want to do is I want to take the derivative of C with respect to E. So this is dC dE. And I've gone ahead and computed it for you here. You might want to go ahead and verify that it's this right over here where I've got this 1 over 2E term. And so what I'm going to do now is do my uncertainty in C. Well, what it is equal to is dC dE times the uncertainty in E. And this is my uncertainty in E, 0.1. I'm just going to take the derivative dC dE. That's this term right over here. And that'll give me the uncertainty in the speed of sound. And what I'm doing is I'm plugging in the values, the known location that I have. So I'm plugging in, for example, E equal to 100, my density of 2000, and my Poisson's ratio of 0.25. And so if we were to go ahead and go ahead and do that, I would find out the value of C, so just plug in the values into this equation right here. If I go ahead and do that, I would get 7746 meters per second. And now I want to know the uncertainty in C, so now I use this right over here. So I plug my numbers into this equation and then multiply that by the uncertainty in E. So I'm going to be multiplying that right there times 0.1 gigapascals to give me my uncertainty in the speed of sound. And the uncertainty in the speed of sound is 3.87 meters per second. So hopefully you kind of see the power of this is that if you just looked at these numbers before you did it, and I said, well, I only know my modulus to, for example, 0.1%. I know it's plus or minus 0.1 gigapascals. Does it have a very big effect on this known speed of sound? You look at it here, it's only about 4 out of 7,000, not that much. But it's not really clear when these equations get complicated. Now, we also assumed that we knew what Poisson's ratio and the density was exactly. Maybe this was plus or minus 0.001, and this was plus or minus maybe 10. We didn't have a very good measuring device. I would just keep adding terms. So I would have dC, d nu, times the uncertainty in the Poisson's ratio, which is this value here, plus dC, d rho, times the uncertainty in rho. So there's my uncertainty in rho. And clearly, as I have more uncertainty in each of my input parameters, I have more uncertainty in my output function. So this is the power in engineering of the Young's modulus. All right, so the last thing I want to mention is just something about total numerical error that comes up. Because one of the things that you realize is that, well, geez, if I had really small step sizes, I wouldn't have much error. Because notice that here's the error that I have, but if I go ahead and start approximating myself closer and closer, I'm going to be getting less and less error. Okay? And so here's my Taylor series approximation, and I realize, if I just go ahead and, for example, move this over here, the smaller this value is, which is the step size, this distance right over there is x minus a. The smaller that is, the smaller I would go ahead and have of my truncation error. Because this right over here is called the truncation error because you're kind of truncating at this point or truncating it at that point right there. Okay? Well, that's true, and so if I look at my error as a function, this is the log of the step size. I just realized small step sizes over here, very small step sizes, I have small truncation error. But what happens is there's another thing when I'm using digital computers is remember my numbers that I can store have a finite number of digits. So for example, maybe my value of x right over there, oh, I don't know, was maybe 2.2, and it's a digital computer, so maybe I could only store it to this many significant figures. And then I was trying to approximate this at 2.1999, right? And so if this is all the number of significant figures I can store at that point, there's going to be an uncertainty there of 0.001, and I can't get any smaller than that. And so if I end up getting, there's going to be a certain amount of uncertainty due to what's called round-off error. And as the step size gets smaller and smaller, this error starts to get larger and larger because I'm subtracting two numbers that are really, really close to each other, and I don't have the precision. And so the round-off error actually goes up as I decrease the step size. And so the total error, which is the summation of these two terms, first goes down and then will eventually go up. So there's going to be this optimum space when I use digital computers of minimizing my total error. I'm minimizing my truncation error, my round-off error. So to minimize truncation error, just go ahead and include more and more terms. And then round-off error, what you'd want to do is store your values with more and more precision. So for example, if you're writing this in, say, a C program, you might go ahead and use a double precision variable instead of just a floating point variable. As we saw in some previous videos, the more bits that I have to store the number, the more digits of precision that I have. Okay, so let's go ahead and review what we talked about. First of all, we saw that Taylor series approximates a function value somewhere else using data at where we are at here, right? So we want to know where it is at some other location or some other point in time. We know that all measuring devices, which is essentially a sensor, okay, there's going to be some uncertainty to them, and that's going to lead to an error in the measurements we make and an uncertainty in what we're trying to know. Measurement uncertainties can be approximated using a first-order Taylor series, so we could find out what the uncertainty was. For example, the speed of sound, when we didn't know what the value of the Young's modulus was. And the last thing we discussed was that total error is the sum of the round off, which is the fact that we have a finite number of digits, and truncation, which is the Taylor series approximation error. And so we know that on digital computers, there's going to be an optimum step size that minimizes the total error. You don't want too small of a step size, and you want too large of a step size.